Hey guys, what's up? Today we're going to look at inverse Laplace transforms. If you recall that the Laplace transform of something like e to the 2t is 1 over s minus 2, then we would say that the inverse Laplace transform of 1 over s minus 2 is Laplace inverse of 1 over s minus 2 equal to 2t. So this idea of undoing a Laplace transform is very similar to undoing derivatives. So it's just what would be the function I took the Laplace transform of to get the function that I have right now. So 1 over s minus 2 must have been e to the 2t, and I took the Laplace transform of e to the 2t to get 1 over s minus 2. So very intuitive, this idea of inverse Laplace transforms. There is a super formal definition of the inverse Laplace transform, but just joking here, we're not going to go through that. So it's not practical for us to use that to solve differential equations. We're going to use this natural idea of an anti or inverse Laplace transform, undoing Laplace transform. So the Laplace transform also has this linearity property that we've talked about before. Linearity meaning we can pull constants out of the inverse Laplace transform and we can break it up over additions and subtractions. So if we pull a constant out, we could say that inverse Laplace of a times f of s plus g of s would be a comes out, and then the summation breaks up the inverse Laplace transform as well. So that just becomes a times f of t plus g of t, where f of t is the inverse Laplace of capital F, and g of t is the inverse Laplace of g of s. All right, so let's look at an example here. The example says find the inverse Laplace transforms of, first of all, 2 over s cubed, and then second of all, 2 over s minus 3 over s to the 4. So we want to look at the inverse Laplace transform of the first one. So inverse Laplace of 2 over s cubed. And we say, what do we take Laplace transform of to get something over s cubed? So recall that Laplace of t squared is equal to 2 factorial over s to the 2 plus 1, which is 3. So that's just 2 over s cubed. Well, that would tell us that inverse Laplace of 2 over s cubed is equal to t squared. So inverse Laplace of the function we have, 2 over s cubed, is t squared. So the inverse Laplace of 2 over s cubed is t squared. All right, so let's look at the second one here. 2 over s minus 3 over s to the 4. All right, so that's our function. We want to take the inverse Laplace transform of that. By linearity, we can pull that 2 out and say that this is inverse Laplace of 1 over s minus 3. And then same thing for the second one. We can say that this is 3 inverse Laplace of 1 over s to the 4. All right, so the first one is actually very straightforward. It's just 2 times e to the 3t, because Laplace of e to the 3t is just 1 over s minus 3. So that inverse Laplace transform is very straightforward from what we know about Laplace transforms. However, the second one is not as obvious. So we have 3 times inverse Laplace of 1 over s to the 4. Well, this almost looks like the Laplace transform of t cubed, but t cubed, Laplace of t cubed, would be 3 factorial over s to the 4. So I'm missing a 3 factorial up here. So what I can do is I can multiply by 3 factorial up there. And then I can divide by 3 factorial, but let me not divide inside. Let me divide outside. So divide by 3 factorial outside. Then I can take the inverse Laplace transform and get t cubed right there. So this is going to equal 2e to the 3t plus 3 over 3 factorial t cubed. And now we just reduce 3 over 3 factorial. Well, 3 factorial is 3 times 2 times 1, So the 3 here in the bottom will cancel with the 3 up here and just be left with 2 in the bottom times 1. So this is going to equal 2e to the 3t plus 1/2 t cubed. And that's our inverse Laplace transform.